So first order, we have what we call time versus ln of A. Second order, we have time versus 1 over A. And the zero order, we have time versus the concentration. And we have the respective, what we call half-life between them. So for the purposes of making your life a little bit easier for the second exam, I suggest you memorize what is written here. At least in this slide, because that's the one that you're going to use to solve problems. And we solved problems like that last time. Okay, so what we're going to do today is to discuss the energetics and the reaction mechanism. Okay, so during the reaction, if we're going to plot the progress of the reaction with what we call the potential energy during the reaction, this is how it will look like. So as you're going to look at here, okay, there is some instances when the energy is at the highest point. So what do you learn about high energy? Anyone? If you are in high energy, are you in a stable state or unstable state?
It's unstable.
Okay, so most likely you are in unstable, right? That's why they said, I'm so excited. Okay, but that excitement that you have usually, it will just for a while. After some time, you go back to the reality. Okay, so your energy goes down. So the same thing that happened in a chemical reaction. Okay, so there are instances that the reaction is at its high energy level, and there are two things happen. Either it goes back to become the reactants again, or it's going to push through and produce the products. Now, this AB star star here, or the so-called transition state, that is what we call a state that you need to overcome. And there is an energy associated on that. And that EA here, that is your so-called activation energy. I think I have the write-up that I have here. So when you have this activation energy, this is the minimum amount of energy required to initiate a chemical reaction. Now, I'd like you to look at the difference here. So this is the one for exothermic reaction, and this is the one for the endothermic reaction. So as you could see here, okay, the energy level here of your reactant in an exothermic is much higher compared to the energy level in the product side. That's why this reaction, what happened to the energy? Does it release or absorb energy?
It's released.
Okay, so there's an extra thing there, and that extra or the difference of the energy there is being released. On the other hand, if you have an endothermic reaction, okay, the potential of your reactant is lower than the potential of your reactants. So what happened here, the difference that they have there, that's the energy that you need for the reaction to be initiated. So I added the thing here, okay? So the energy is supplied or absorbed in an endothermic system, okay? So if we're going to look at here, which is more stable, the products or the reactants in an exothermic reaction? And which is more stable, the reactants or the products in an endothermic reaction? So which is more stable here?
The products.
Okay, the products is the one that's more stable. Here, it's the reactant. Why? Because they have low energy. Okay. So if the product is more stable than the reactant, the energy is released. If the reactant is more stable than the product, then the energy is absorbed. Now, they found out that there's a temperature dependence of the rate constant. So the rate constant that we have is what? The small k. So they found out as the temperature increases, okay, the rate constant value also increases. So they end up with getting this so-called Arrhenius equations, where the K is equals to A, just showing you what they are, which is what we call the frequency factor, times E. Okay, you know E, right? The inverse of Ln raised to the activation energy divided by R and T. So what happened here, if you're going to look at the alternate form of it, it looks like this. And as you could see, which is the Y here and which is the X? If you're going to put it equals to this equation of the line, you will see that the 1 over T is your X and the L and K is your Y. And the slope that you have here, okay, that is just the activation energy divided by the R plus the Ln of A. And if you're going to rearrange them, okay, this is what you get. So this is the Arrhenius equation. Now, is this new to you?
No. No.
Okay. So this is just similar to your, if you have your first exam, the Clausius-Clapeyron equation. What changed? Instead of the rate constant here, in Clausius-Clapeyron, you have what?
The pressure.
The pressure. So see how they do science? They adopted one equation, they just exchanged one of the factor there, and then they can have a new equation. So here, they have what we call the Arrhenius equation. And an Arrhenius equation deals with the relationship of the rate constant with the temperature. Okay? So if we have, let's say, one problem similar to this one, maybe we can do this. It's similar to the, what we call, what do you call that? Clausius-Clapeyron equation. So you're given here a rate constant at a given temperature, and you're asked what's the rate constant when the temperature is increased to 350, given the activation number is 50.2. So what do you expect? From 298 to 350, what's the new K? Will it be higher or lower than 3.46 times 10 to the negative 2? Anyone? Will it be higher or lower than 3.46 times 10 to the negative 2?
Be higher.
Okay, it will be higher because as you could see here, as the temperature increases, the rate constant also increases. Okay. Now, if we're going to solve this problem, we just follow what we have. So we can put here the Ln of, we could say K1 over K2. And then if you follow the equation that we have there, so this is EA over R, and then you have 1 over T2 minus 1 over T1. And then you have to, you don't have to convert this already to K because they're already in K. So all you need to do is plug in the given value that you have. And what's the R that we use here? Okay, since we have a joule, so you have here at 8.314 joules k mole. So all you need to do is we have to multiply this with 1000. And then this will be 1 over. So this is 350, right? What do you get on all this part here? Anyone? Forget my calcu. Anyone? What's the calculation that you have on this part? Because this one will remain like this. But this one, when you incorporate everything, what do you get? So this is a small number minus the big number. So that would be a negative. Negative what? Do you get negative 3.01? Anyone? Did you get this? Anyone? Are you still there?
Yes, negative 3.010. Yes.
So the way that we're going to do it is we're going to remove the ln here by and that would be equals to what? 0.0. And rearranging this thing, what's K? So K is equals to, please do the calculation, okay? You will only survive the course if you do your part. What's the calculation? So even though online, I want you to do it real time.
The 0.072.
Point, is it 0.0 or 0.702? What,
0.702.
okay. Now we go back to our statement. So if we're going to look at this, this is really like this, right? Now when you increase the temperature to 350, it goes to 0.702. Now, should there be a question like this in the exam, I hope you will get it right at this time. Okay. So question. So the key here is this one. Should there be a problem like this in the exam? Question? So the next thing that we're going to do has something to do with orientation. Okay? So we all know by now that when reactants react with one another, they produce products. And we just learned today that for the reaction to proceed, they have to overcome the so-called activation energy or the heel. Okay? Now, in addition to that, we have to look also the importance of the so-called molecular orientation. So molecules are in three-dimensional space. Okay? So it's not the way that when you mix them, they will just react with one another. What you have learned in the kinetic molecular theory is gases usually what? Collide with one another. But if we look at the importance of the molecular orientation, they have to have this so-called effective collision. Okay? So when we're talking about effective collision, it has something to do with the orientation on the way atoms in a given molecules collide with atoms in another molecule. So for instance here, when CO reacted with NO2, for the reaction or collision to be effective, it has to be in a way that, what do you think is this black thing here? It has to be in such a way that the black thing here, which is your
Oxygen.
carbon,
Carbon.
collide with oxygen for the collision to be effective. So the way that that happen here, so when this approach it this way, okay, it's going to give up the NO, producing CO2 and NO. But if you're going to approach it this way, where nitrogen is the one colliding with your carbon, the resulting reaction is just not going to happen. So if the collision is carbon of CO reacting with the nitrogen of NO2, there will be no effective collision. So the term that we have there is ineffective collision. So that means they have to follow a certain molecular orientation for the collision to be effective. Okay? So that's the importance that we have here, that for the reaction to push through, the effective collisions must be observed. Now we go to the topic of the so-called reaction mechanisms. So when we look about, when we talk about reaction mechanisms, this is the one wherein you're trying to look at the step-by-step reaction that happened during the reaction. Yes? Someone is raising the hand. I don't.
Sorry, Professor, wrong.
Huh? Question. Question.
Miss, yeah.
Hmm? What's your question? Okay. So
Professor, no question, but misstep, that's all.
what?
Professor, are you hearing me? No question, just mistake, Professor.
So when we're talking about this so-called reaction mechanism, okay, we're talking about the exact thing that's happened during the reaction. So usually what do we see? Here we just see what? The overall balance equation, right? So what does the balance equation tells us? It just tells us the beginning and the end of the reaction. But the sequence of steps that happen during the reaction, we don't know. And to know that sequence of elementary step, as we mentioned here, is to write the so-called reaction mechanism. So they said here, the overall progress of a chemical reaction can be represented at the molecular level by a series of simple elementary steps or elementary reaction. And the sequence of elementary steps that leads to product formation is the so-called reaction mechanism. So as I have told you, a balanced chemical equation is just a description of the overall result of a chemical reaction. However, what actually happened on the molecular level may be more involved than what is representative by a single equation. Okay, so the reaction may take place in several steps. So let's say you go to a trip from New York to DC. Okay, so the overall story that you have there is you just have what? You went from NYC to DC. But if you're going to look at the steps that happened during the trip, so maybe you have a hard time getting out of the city. The traffic improved when you go to when you arrive at New Jersey. It further improved when you pass by Pennsylvania and so on, or we could say Delaware or Maryland. So that's what we call elementary steps that happen. So for instance, here, this is the overall equation. But they found out during the reaction, this compound was detected. Unfortunately, you don't see this compound in the overall reaction. So what you need to do is you need to know the reaction mechanism. You need to know, okay, what are the steps that happen during this reaction? So if you're going to look at the mechanism, okay, the first elementary step that you have there, you have the 2NO. It reacted to produce N2O2. Now in the next elementary step, your N2O2 reacted with oxygen to give you 2NO2. So the story that you have here, you cannot say, based on this chemical equation, the 2NO reacted really with oxygen. Because if you're going to look at the full details of the story, oh, the 2NO reacted with one another, producing N2O2. And that N2O2 reacted with oxygen to give you 2NO2. So you could see now, you have what? A full picture or a picture of the whole story of the reaction. Okay, so for instance, I think I have some, before I show you the molecular view on this. So what happened? If you add all the elementary step here, what it gives you is the balanced chemical equation. So if you're going to look at this at molecular level in terms of the mechanism, okay, so the 2NO produces to give you N2O2. And then your N2O2 reacted with oxygen to produce 2NO. So if you're going to look at the overall reaction here, you can find this in the products, you can find it in the reactant in the next step, you can cancel them out. And what you have at the end is this 2NO here reacting with this to produce this one. Now the term that we have for this, one that appear in the initial reaction and then disappear in the succeeding reaction is what we call intermediates. So intermediates are compounds that appear in the initial reaction as a product and then disappear as it acts as a reactant in the succeeding reaction. So intermediates are species that appear in a reaction mechanism but not in the overall balance equation. So if we're going to look at the example that I gave you, if you are asked what is the intermediate in this reaction, it's N2O2. An intermediate is always formed in an early elementary step and then consumed in a later elementary step. Okay? So question on that. By now, you should know that when you're given a balanced chemical equation, most likely there is more story behind it. So you look at what we call reaction mechanism. So the reaction mechanism tells you the elementary steps that it has. Okay. Now, reaction mechanism, that's most challenging when you go to Orgo. Any one of you here taking Orgo after Gen Chem 2? Are you going to take Orgo? So in Orgo, you will have this so-called reaction mechanism. You will have this so-called arrow pushing or electron pushing that they have. Okay. So in what we have discussed, the elementary steps that we have will show us that there are chemicals that are formed in early elementary steps and used up. Now, these chemicals or compounds, they don't show up in the overall balance equation. And we call these chemicals as the intermediate. Okay. So later on, as we go on more example, I will ask you to identify if there's an intermediate in a given set of elementary steps in a chemical reaction. Now, the next thing that we can discuss on is the so-called molecularity of a reaction. So this is just the number of molecules reacting in an elementary step. Okay. So if you have a unimolecular reaction, it's just elementary step with one molecule. If you have a bimolecular reaction, it's elementary step with two molecules. If you have a thermomolecular reaction, you have an elementary step with three molecules. Okay. Now, what does this tells us? This unimolecular, bimolecular reaction. So it can be like this. If you have a unimolecular, you only have one reactant. Okay. You only have one molecule. And the rate just depends on that molecule. Now in bimolecular, you can have two molecules of different type or one molecule, but of the same type. So my question here, what is the molecularity of our elementary step here? The first one, how do you classify this? Is this uni, bimolecular, or thermomolecular? So this is 1, 2. So that's a bimolecular. And this is the bimolecular wherein you have one type of molecule. Because you have the same molecule, you only have two molecules. Now the second one, okay. The second one is what? What is the second one? Is it also bimolecular? Anyone? So you have one type of molecule.
Also bimolecular.
Okay, and another type of molecule, so that is also bimolecular. We're just showing you the so-called molecularity of a reaction. Now, the relationship that they have here is this. Based on unimolecular, usually you have what? A first order overall reaction. If you have a bimolecular, you can have a second order overall. So when you say overall, it includes the A and the B. And it can also be a second order wherein you only have one, what we call type of molecule. Now, how are we going to write the reaction mechanism? Okay, so this is what we call the steps. The sum of the elementary steps must give us the overall balance equation. So it's here. When we add these two, we give us the overall equation. Now it also says there, the rate determining step should predict the same rate law that is determined experimentally. So we have this so-called RDS, the rate determining step. Now you may ask yourself what it is. The rate determining step is the slowest step in the sequence of steps leading up to product formation. So how do we do this in real life? So you are driving in expressway. Okay? How fast you drive is determined by the slowest vehicle. Right? When you go with what we call the traffic, you cannot run faster compared to the one when there's no traffic. So the one that determines how fast you run or how fast you drove your car is determined by the slowest what we call running vehicle in the expressway. Or let's say if you are in a cafeteria, but we don't have cafeteria at this time. So if you are in the line, okay, how fast the line will go is determined by the slowest person in the line. So usually if you have a slow person in the line, a slow moving person in the line, okay, the line will also go slow. So the same thing in the reaction, okay? How fast the reaction will go will be determined by the slowest step. And usually the slowest step will have the same rate law as the one that we determine experimentally. So as of now, rate law can only be determined experimentally. But if we have the reaction mechanism, there's another way to determine rate law. And that is by the rate determining step. So in this here, in this elementary step that we have here, we need to know which is the slower one. Because the slower one will be the one to predict the rate law. Okay? So let's try to look at some example. Or maybe before we go there, we just look at the sequence in the step of studying the reaction mechanism, how they end up studying this one. So usually they just try to measure the rate of a reaction. And then based on that, they were able to determine the different elementary steps. So they found out the slow elementary step, and that's the rate determining step. And from that, they postulate a reasonable reaction mechanism. So for instance here, so you have two steps in the gas phase decomposition of nitrous oxide. Are you familiar with the nitrous oxide? What's the common name for that? Anyone? It's used in dental offices.
Laughing gas.
That's the laughing gas. Okay, N2O. Now they said it's happened in two steps. N2O breaking down to N2 and oxygen atom. and then N2O reacting with oxygen atom to produce N2 and oxygen. Now, they found out that the rate law is this. So you are asked the given following question. What is the equation for the overall, what is the equation for the overall reaction? So what you do is, you add them. So what is cancelled out?
Oxygen.
Oxygen. And you end up with 2N2O producing 2N2 and oxygen. So that's the overall equation. Do we have an intermediate?
Oxygen.
Do we have an intermediate? Yes or no? The answer is yes, and it is the oxygen atom. Why? You see it being cancelled out in the early step, or produced in the early step and then used. So I would say appear, disappear, or you could say produce and then use. Now, this is the thing. What can you say about the relative rates of step 1 and step 2? Which step is slower? Or which is the rate determining step here? So you're given here the rate law. And as you could see here, this one is the only one that has here. So I would say what? Step 1 is slow. If I could answer, okay. Anyone? Yes? Question?
Oh, Professor, please could you explain? I don't understand.
I'm already explaining it. Okay?
Could you repeat what you said, please?
So as I have said here, since you're given the rate law here, and what does the rate law says in the previous, what we called here? The rate determining step should predict the same rate law that is determined experimentally. So you determine the rate law here, it's equals to this one. So that means you have to look at the reactant that contains N2O. Now, both of them contains N2O, but what's the giveaway? It doesn't have the oxygen. That's why you could say the first step is the rate determining step. And that's the one that is slow. Okay? Why is it the slower one? Because the rate law says that the rate law set is K times N2O. And that's the only one that contains N2O. Step 2 contains N2O and oxygen. So if we're going to look at the relative rate of step 1, step 2, this is the slower step compared to this one. Understand?
Professor, so the answer to C is the first reaction.
No, it just says what's the relative rate. So step 1 is slow. That's why I put the slow there.
Okay.
Everybody got that?
Yes.
Okay. And then in addition to that, we also have this substance known as the catalyst. So what does the catalyst do? Okay. The catalyst just hastens the reaction. So it's a substance that increases the rate of a chemical reaction without being consumed itself. Okay. And the way it affects what we call the Arrhenius equation, it lowers the activation energy. Okay, so if the activation energy is lower, the rate constant increases. So when you have a catalyst, you have an alternative pathway. You have a different reaction mechanism. And if you're going to look at this, so I want you to change, okay, the one that you have here. Because if you're going to compare an uncatalyzed and a catalyzed, what we call transition state, okay, the catalyzed one would have a lower activation energy. But I think in your thing here, it's the other way around. So this is the catalyzed one, wherein the activation energy is less compared to the one that is not catalyzed. Okay, so it provides an alternative pathway. It provides what we call a different reaction mechanism. Okay, now if you're going to look at this catalyzed reaction, they usually be faster compared to the one that we call that is not catalyzed. And if I'm going to ask you, what's the best example of this catalyst? Can you give me the answer to that? What are known as the biological catalysts? Anyone?
Enzymes?
So enzymes are biological catalysts. Okay. So enzyme is there to help you break down some stuff. And usually, how do you name enzyme? Usually they end up in
With an
ACE, right?
ace?
Enzymes usually end up like ACE. I don't know if you noticed that. Okay. Now, the catalyst that you have, remember, you have here what we call the transition state. And sometimes we could say the transition state, that is also your intermediate. That's where intermediates are formed. Okay. So if you're going to look at the rate that you have there, the rate of the catalyzed one is much faster than the uncatalyzed one. So I'll give you an example later on of elementary step with both the catalyst and the intermediate. But the way that we have this catalyst is it just makes the reaction faster. How? It lowers the energy, activation energy. And when the activation energy is lower, then there can be different mechanism that happen. There's a what we call alternative pathway that the reaction goes, which make it a little bit faster. Okay. Now, catalyst is useful, especially to speed up the reaction. Okay. So if you're going to look at the industry that you have there, so if you're going to look at this, the activation energy here of the catalyzed one is lower than this one. So you can have a heterogeneous catalysis wherein the reactants and the catalysts are in different phase. So they usually has this applied in industry. Okay, the Haber synthesis of ammonia. Okay, they put some what we call solid catalyst there, because the Haber process usually you just mix hydrogen and nitrogen at high pressure and temperature. But what happened? They developed some solid catalyst to produce ammonia. Okay. And then you also have this production of nitric acid by Oswald process and the so-called catalytic converters. Now for homogeneous catalysis, usually this is useful for liquids. Okay. Like what you see in acid catalysis and base catalysis. So if we're going to look at the enzyme catalysis that we have, so you have here a substrate that acts on the enzyme. And once, okay, the enzyme acts on the substrates, is going to produce the products that you have. Do you know the chemical explanation why when you put meat with what we call papaya and what else? Pineapple. Do you know why they do that? Do you know the chemistry of that? Anyone? You know papaya, right? Anyone?
Yes.
Papaya
Yes.
is, okay? So the way that they do is they have some catalysts that they have that degrade the meat. Okay. So I think here they have papain and here they have bromelain. So the enzyme, these enzymes that they have, it acts on the meat, okay, breaking down the meat fiber that it has, resulting to a much more tender meat if you mix them. They just don't mix them because they're what we call fruits, but the enzymes that these fruits contain act on the meat. And also, what's the difference of these so-called ruminants and human beings? Are you familiar with ruminants?
Isn't that found in cow or digestive
usually-
system?
These are what we call animals that just thrives on what we call plants.
It's the extra digestive enzymes found in cattle, right?
Yep. What is that? What is that enzyme? The human beings don't have that. That's why if you eat fiber, what happens? If you eat fiber as human being,
They break down cellulose that we don't.
okay? So if you are a human being, you eat fiber, what happened to the fiber?
Insoluble.
It comes out of your body as a fiber. Because you don't have, what enzyme is that? Cellulase that acts on the cellulose. But if you are a ruminants, they have cellulase, so they can break down the cellulose, so it will not come out as fiber. So that's the reason why if you have digestive problem, they ask you to take more fiber. Okay, so another thing that we can look at here is the hexokinase, the binding of glucose to the so-called hexokinase. Okay, and also some of these diseases is due to what we call the absence of some glucose. Are you familiar with the lactose intolerance thing?
Yes.
What is the lactose intolerance? These are people that don't have lactase. So they cannot break down lactose to, lactose is a disaccharide that is made up of glucose and the lactose. So if you're lactose intolerance, you don't have the ability to break down the sugar into glucose and galactose. Okay. Now, for some specific example that I have promised you, I'm going to go to the whiteboard. It's not in the lecture notes that we have. So I'm going to give some example here so that you will be familiar with this so-called intermediates, catalase, or not catalyst and other stuff. So let's say we have this. NO2 plus F2 producing NO2F plus F. And then in the next step, you have F plus NO2 producing NO2F. And then this is the slower one. And I could put away fast. So if it's blank, you can assume it's fast. Okay, as long as you know the slow, you're fine. So the question is, what is the overall reaction? Is there an intermediate? Is there a catalyst? And then write the rate law.
Are we doing this now, Professor?
Do it now. Okay, try to do the sheet work, and then we go together answering it.
Professor.
What?
Sorry. How did you know that this one was slow and the other one was fast?
I gave it to you.
Oh, so it's part of the question.
Yeah.
Oh.
Because I will not be able to answer it if that's not given. So what's the overall reaction? So if you're going to look at the overall reaction, so this is
2
step
NO2.
and this is step 2. So you can just add them and then look at the ones that are common on both sides. So as someone said, 2 NO2
Plus F2
plus F2
produces 2 NO. Sorry, 2 NOF.
2 NO2F. So that's the overall reaction. Do we have an intermediate? Anyone? Do we have an intermediate?
Fluorine.
Okay, we have. It's the fluorine atom. It's one that appear in the initial step and then disappear. It was produced and then used. Do we have a catalyst? The answer is no. Usually, catalyst is present at the beginning and present until the end. You will see it in the reactant, in the initial step, in the product, in the final step. So we don't have a catalyst. Now, what is the rate law here?
K equals concentration of NO2 times F2.
Okay, very good. What's the guide there to give us the rate law? The word slow. That's why I told you, if those words are not there, I cannot answer that question. Either you're given the rate law and you determine which reaction, which step is slow, or you're given the elementary step that's slow, okay, and then get to the rate law. Question before I give you another one and end the chapter. Question before I give another one. So the next one, I'm going to give you these elementary steps here. This is O3. And then you have ClO plus O. and you're given the rate law as this. So the question that you ask, what is the overall reaction? What's the intermediate, if there's one? What is the catalyst, if there's one? And write the mechanism of the reaction. So you just put here, which is the slow among the elementary steps that you have. Let's see if we got that. So if you have this stuff, what do you do? You're just going to add them. So try to find any common species on both sides. So what are those common species on both sides that you can cancel out? So you have the CLO. What else? Is CLO the only one that is common on both sides of the reaction? Or if you're going to add the reaction?
You have chlorine gas in the as a reactant in the reaction.
So if you have that, what do? You end up with O3
O3,
reacting with
O3 plus O,
O,
and
produce
2O2.
2O2.
So this is the reaction of ozone. Now, what is the intermediate? What is your intermediate?
Chlorine and chlorine oxide.
So your intermediate is ClO. Do we have a catalyst? The answer is yes. And that's your Cl. Now look at the difference between the intermediate and the catalyst. Do you see the difference between the two?
Absence of oxygen in catalyst.
Okay. So if you're going to look at ClO, it appears as a what product? It is produced in the initial step like this and then used up. Now for the chlorine, it was used in the initial step and then produced in the succeeding step. Remember, the definition of a catalyst is always there throughout the reaction. So that's the main difference between the two. One is produced and then used, and the other one is used and then produced. Are we clear on that? Are we clear on that?
Yeah.
No, Professor, I'm not.
So again, an intermediate is something that is produced in the initial step and then used up in the succeeding step. Like ClO, you produce it and then it's used up. Now, a catalyst on the other hand, it is being used in the initial step, like Cl here, and then produce in the succeeding step, like this one. You see Cl in the reactant side, so it's being used, and then you see Cl in the product side, in the succeeding step. That means it's produced. So if you're going to put the overall reaction for this one, it looks like this, wherein you add everything, right? But what is common? You see this one on both sides, you cancel it. You see this side on both sides, you cancel it. But the elementary steps tells you at what steps they are the reactant and what step they are the product. If they are part of the product initially, okay, and then become part of the reactant on the succeeding step, that's your intermediate. If they're part of the reactant in the initial step and part of the if they're part of the reactant in the initial step and then part of the product in the succeeding step, then they are the catalyst. So are we clear on that? If you still say you don't understand, then I don't know how to simplify it. And you say you don't understand and you get 100 in the quiz, then I don't know how to explain it also. Because you have a quiz. Okay?
Professor, what's the mechanism?
What?
The last question. What's the answer?
We're not done yet. Okay?
Oh,
So
oh,
how are we going to write the mechanism here? Where do we put the word slow? That's the only way to do when you say write the mechanism. You have to find the rate determining step. So where is the slow? In the first step or the second step?
Step 1.
Just wait. Just maybe I like it a
Step
poll,
1.
so everyone will answer. Because the problem with you is you're not participating, and then in the exam it will be shocking. So maybe let's try this one. Let's see how many of the 29 students are really participating. So what is the rate determining step? Is it step 1 or step 2? Because you are going to have a questions like this, which is usually what, 5 to 10 points in your exam. So where are the 19 students? Okay, yeah. So what is the rate determining step based on this one? So where are the 10 students? Okay, only 19 participate. So where are the 10 students that's supposed to be online? Okay, so I'm going to end the poll. So this is the answer that you have. So what is the rate determining step? Usually, if you're going to have an answer here, you base it on the given rate law. So based on the given rate law, find where those species are as reactant. So it's the one here and here. So you could say this is the slow and this is the fast step. So that's how you write the mechanism. Question?
I have a question, Professor. So pretty much when we get that type of question that you just asked, it's always going to be the answer will always be where it says rate equals.
Yeah, because that's the rate law. So we have discussed that the rate determining step is the slowest step. So either you're given these words or you're going to provide those words. But if you're going to provide those words, you're given this one. Or if you're given these words, you have to supply the rate law.
And this is what we always start with, correct?
Yep.
Okay.
That's why either you write the reaction mechanism from the rate law or you provide the rate law from the given mechanism. So when you're given what we call the mechanism here, okay, what happened is you can provide it. If you're given the mechanism, you can provide the rate law. All you need to do is find the slow step and write whatever reactants that the slow step has. So let's say you don't have this. You're given this one, so all you need to do is rate, and then there's a K always in the rate law. You put Cl and ozone, and you end up getting the rate law. So you have now an alternative way to determine rate law. Before, you can only determine it experimentally. Although, the way you determine the slow and fast elementary step is also experimentally. So this is the essence of doing this, what we call reaction mechanism. Question? Anyone? The others? So if none, we just finished chapter 13, and we're going to proceed with chapter 14. The most important, we could say, chapter here in this course. And if we finish this by next week, we might have our exam on either the 23rd or 30.
In that exam, would it be based off chapter?
It will be 13 and 14, the next one.
Okay.
So, chemical equilibrium. So, this is, we could say, an abstract concept, but you have already encountered chemical equilibrium as early as the first day of class. Okay. So, before we go with this concept of chemical equilibrium, I want you to get your calculator. And we're going to play some sort of an exchange game here. So we have box R and box P. So what happened? 1/2 of anything box R has will go to box P. And 1/4 of box P has will go to box R. So let's say there's 40 items in box R and no items initially in box P. So after the exchange, how many items does each box has? So 1/2 of 40 will be what? Anyone?
20.
Okay, 20. 1/4 of 0? Nada. So after the initial exchange, you have 20 items in box R and 20 items in box P. Do you follow? Do you follow?
Yes.
Yes.
Okay. Now 1/2 of 20 is equals to what?
10.
Okay, so you have 10. And 1/4 of 20 is
5.
5. So after the exchange, you will have here what? 15. And you have here 25. Now, the next thing that we're going to do is we're going to fraction, to get the fraction, we're going to what we call round it up to whole number. So 1/2 of 15 is what? 7.5. When we round it up, 7.5 is equals to what? Let's say 8. What's 1/4 of 25?
6.25.
1/4 of 20.25 times 25, that is equals to what? 7 or 6?
6.25.
6.25. So that's 6, right? So after the exchange here, this is what? 13. And this is 27. Am I right? So 1/2 of this will be 6.5. So that would be what? 7. And 1/4 of this, so if we go with 28, that will be also 7, right?
Wait, Professor. Professor, where did you get the 13 from, please?
Where did I get the what?
13.
So you have 15 here, you lose 8, you gain 6. That is equals to what?
13. My question is where did you get the 6 from?
What's 1/4 of 25?
I just did it and I got 100. So I don't know.
What is 1/4 of 25?
6.25.
So you know where I get my 6? Do you follow?
Yeah,
Do you know where
I
I get
figured-
this number
I got
here?
Wait, Professor.
Okay?
Professor,
Yes.
I have a question. Okay, so where's the 25 from?
When you add 10 to that and you lose 5, how many do you get?
Oh,
No. That's why you listen. What did I tell you at the beginning? 1/2 of box R goes to box P and 1/4 of box P goes to box R. Are we clear on the mechanics? What are these numbers that I have here?
but Professor, 8 plus 6 is 14.
What?
8 plus 6 is 14.
I don't get what you're saying. You're confusing the class. So listen, okay? What's the name of the game? Chino, if you have question, can you just send it to me directly because you're confusing the class.
what she's
And,
saying is
and I'm trying to save the class, okay?
what
You
I
asking
think.
questions, sometimes it just mess up everything. So listen, okay? We have items in box R. What we do, 1/2 of that items go to box P. And then in box P, 1/4 of that items go to box R. So initially we have 40 and 0. What is 1/2 of 40?
20.
What is 1/2 of
20.
40? Anyone? What's 1/2 of 40?
20.
20.
20.
That's why I listed here. So as you could see here, 20 of 40 will go there. And then 0 of 0 will go here. So at the end, we get 20 and 20. Are we clear on that?
Yeah.
Okay. And then we go to the next exchange. What is 1/2 of 20?
10.
10.
10.
What is 1/4 of 20?
5.
5. So as we go on, you lose 20 here, but you gain 5. So that will give you
15.
15. And then you have here, you lose 5, but you gain 10. So you have 25. Are we clear on that? Because I don't want students who don't listen and out of nowhere ask question. It confuses the dynamics of those who are listening.
Professor, I think
Yep.
what you were trying to say earlier was that 8 plus 6 is 14, not 13.
No, you don't add 8 plus 6.
So then, okay, I'm
What you
confused
have?
now.
8, you lose 8 here for the 15, but you gain 6. You know what I mean? You lose 1/4, you lose 1/2, but you gain 1/4 of P. So what is 15 minus 8?
I got it. Yeah, I see now.
Okay? Because this is crucial for you to understand the concept of equilibrium. So 13, 1/2. Oh, so are we in the same boat now in this number? Everyone clear on this? Hello.
Yes.
Yes,
Yes.
Professor.
Yes.
We are here.
Okay. Now the question that's being asked now, okay. After the exchange, you still have 13 here, right? And then after the exchange, you still have 13, and it will just be the same like that, right? Now the question that I will ask, is the 27 items here the same as the 27 items here? Yes or no?
No.
How about the other? Maybe I can do a poll. How about the others? Do we have this, what we call the same 27 items before and after the exchange?
No, they're not the same.
Okay. How about the others? Is the 13 here the same as the 13 here? Is the 13 here the same as the 13 here? Yes or no? The answer is, type it in the chat. The answer is no. Why? Because at least 7 items from the previous 13 went to box P. Okay? And 7 new items came here. Now, if you're going to plot this, so I have your number of exchange, and then I have your number of items. So one I start with 40, the other one I start with 0. And then in the first exchange, what will happen? Both of them end up with 20. Okay? And then the second exchange, one is what? 15. And the other one is 25. Right? And in the next exchange, one is 13. And the other one is 27. And then it will remain the same. So what happened? So if we're going to plot this, what is this line represent? This line represent what box?
The products.
And if we're going to represent this one, so at this space, you now reach the so-called equilibrium phase. Okay? So what is this equilibrium space? So this is what we call state in which there are no observable changes as time goes by. So where do we get this meaning here in the exchange? No observable changes as time goes by. There are two situations there that tells us that thing. What are those two situations? The number of the boxes remains the same, and the number of exchange remains the same. Do you get it? Everybody get it? that once you reach here, the number of exchange is the same and the number of items in the box are the same, because that's what chemical equilibrium is. It achieves when the rates of the forward and reverse reactions are equal. So where do you see it here? The rates of the forward and backward reactions are equal. That is when you have this 7. Do you follow that? And the other condition that we have here is when the concentration of the reactants and product remain constant. And where do we see it here? That's the 13 and the 27, the one that you see here. So we could say from this part here, you reach equilibrium. Now, as I told you earlier, we already met equilibrium since the beginning of the semester. Okay? What process is this one? From liquid to gas, which is part of your exam 1. That's your vaporization. Now, what's the process when you have gas going to the liquid? That's condensation. Okay? So when does the equilibrium reach? When the exchange that they have is the same. That is when you have what? A closed container. And what did you achieve there? The vapor pressure. Okay, so that's a physical equilibrium. You also have a chemical equilibrium, just like the one shown here in the photo. So you have N2O4 producing NO2, and this is the brown gas that is formed there. Now, what do we know so far in the reaction that we have? Always like this, right? Reactants going to the products. And just like the name of the bond, it's one direction. But for chemical equilibrium to achieve, you have to assume that the reaction is what we call reversible. So when we say reversible, your products can also be your reactants to produce products, which is your reactants. So what does it mean? The reaction can go on both directions. In fact, you seldom see a one direction reaction. Most of the reactions are what we call reversible. Remember, if you have in the closed container, what will happen? Initially, if you just have what? Water on it. So you have a big container there, you close, you have a beaker. So initially, what do you have? If you just have the liquid there, everything goes to gas, right?
Yes.
Now, what happened when you have too much gas? What happened?
Okay. Condenses to form liquid.
They condenses to form a liquid. And there will come a time that the rate of vaporization is the same as the rate of condensation. So that's when you achieve equilibrium. Now, what happens if you don't have the closed container? Your reaction will be one direction. Because what happened there? Your liquid will continue to vaporize until there's no more liquid. Why? Because they are all escaped already. It's not a closed container. So you have no gases that was collected. When they escape to the gas, bye-bye. They're gone. But if you close the container, the gases are collected. And once there's enough gases, okay, they condense back into liquid. So that's where what we call equilibrium. In chapter 12, you also attain equilibrium. Remember when you have a saturated solution? What are the two processes that's happening there? You have dissolution and recrystallization. So what is dissolution? your solid is dissolved in the solvent, or your solute is dissolved in your solvent. What is your recrystallization? The dissolved solid recrystallize back into solid. So when you have a saturated solution, there's equal rate of dissolution and recrystallization. Again, you have the equilibrium. Okay, so if we're going to look at this, what we call chemical equilibrium, it can have different starting point. Okay, let's say if we have this reaction, so you see now you have a double arrow direction here. So what does it mean? In the conventional write-up, this is the reactants and this is the product. But in a reversible reaction, this can also be a reactant and this is the product when the other one is the reactant. Okay, you can have different starting point. Let's say you just have your NO2. So NO2 you have there, initially you don't have N2O4, but after some time you allow them to react, you reach the equilibrium. And then you can start with N2O4. So this says N2O4, and then after some time, their concentration remains the same. So that's the time when they reach equilibrium. Or you can have a point wherein both of them are starting with some initial amount, but at the same time, after some time, their concentration don't change. Now, what did they found out here? When they try to monitor the changes in the concentration, when they tabulate it, before I go there, this is what happened. Okay, whatever the concentration that they have at equilibrium, when they get some sort of a ratio of the product over the reactant, they end up getting what? The same value. Okay, and what is this value that you have here? That's your K. And how are we going to write the K that we have here? So this is just equals to the products of the products over the products of the reactant. So if you're going to write this one here, you write it in that way. Or you follow the pattern that we have. If we have this reaction, the K that you have, you will write it like this. So the products of the products over the products of the reactant. Okay. So that is based on the so-called law of mass action. So it's all about the K value here. That's why I always tell my students, this course is all about K. And your role is your DO. And it's up to you, where are you going to place O? Is it before K or after K? So after the exam, I think most of you, where is your O?
The other side of K.
It's either you're like this or you're like that. So after the first exam, where do you go? I think most of you are here. You know what KO means? Yes. You have a question, Tigran?
No,
At least you're here, Tigran. You're the highest. That's why the role that you have in this course is, where is your O? Is it before K or after K? Now, right now, most of you after the first exam, it's here. If you don't know what KO means, if you are fond of boxing, where my countryman Manny Pacquiao is very popular, so that means knockout. And you know what OK means, right? And unfortunately, this course is all about K. Today, you're going to learn about KC, KP, And then in chapter 15, you have Ka, Kb, Kw. Okay. Chapter 16, you might have Ksp, Kf. So it's all about K. And as I've told you, the concept of the concept of equilibrium has already been discussed as early as chapter 11 and chapter 12. You didn't what we call discuss it in chapter 13, but there's a K there, a small K. And in fact, Gen Chem 2 is just all about K. And the challenge that I have to my students is to place the O either before or after K. Question before we take a break, and I'll give you the quiz. Yes, my favorite student. Question, Chino.
Professor, I have a question. So for the other one, for the rate law, do we have to include the coefficients or no?
No.
Oh, so it's only for chemical.
I wanted to go back to the lecture there. Because you don't see any what we call rate law equals to A raised to the A there. It's what? Anyone? Rate is equals to K times A raised to what? Is it letter A?
I don't remember.
Why? Because it doesn't include the coefficient. If you're listening, it's not included the small a slash b. Because if you have there, that's rate equals to K raised of A and X. Is X the same as A? Are their letters the same? Common sense will tell us they're not the same. So that means the coefficient doesn't play a role on the rate law. Okay, there you go again. Those stuff should be asked during that time. Because what you ask is just creating confusion to some of your classmates.
Professor, what is X and Y?
Wait. It may clarify you, but to them, it's more confusing. Okay? I tried to save the whole class here.
Okay. What is X and Y?
You know, Chino?
No, Professor, I was late, so I didn't listen.
No.
I was late.
That was discussed 2 weeks ago.
Oh,
Okay?
I didn't take notes. Sorry.
Well, it's not my problem. Okay? Please. Now I'm beginning to suspect really you perform good, but you ask questions that's just I don't know. Okay? So if you don't take notes, then it's not also my job to repeat this again. Okay? It's time for us to take the quiz. So I'm going to open the quiz. So how many minutes do you want for the break? Because that's the time I'm going to give for the quiz. 20 minutes enough? Class?
Yes. How many questions?
All of these are the multiple choice question. Usually what I do is the calculations is on the second one. So I can give you all the time that you need. But this one, this is 5 question. Oh, there's one calculation here. But this is the what we call the typical rate law determination, which you should be able to answer because this is what we call still a multiple choice question. So 20 minutes fine. We resume 10:56. That's okay?
Yeah, that's good.
So even though it's a calculation, but it's still a multiple choice, what we call question. Okay, so 20, just wait. I don't have my mouse, that's why it's put me a time. Edit the test option. So that's 20 minutes. Okay, making it available in 3, 2, 1. Should be available now. So we'll resume class at 11. We can continue. So as I mentioned, if we have the so-called chemical equilibrium, which is K, this is just the ratio, okay, of the products over the reactant. So if you're going to look at the value of K here, come on, writing part. You're just looking at the ratio of the products over the reactant. So what does it mean? If you have more products than the reactants, your K value would be more than 1. And what will happen there is it favor the forward reaction. So if it favors the forward reaction, you have more products compared to the reactant. If you have more products, so that means your K is more than 1. Does that make sense? If the forward reaction is favored, more products will be formed. So if more products will be formed, that means the value of your products, okay, is higher than the value of your reactants, resulting to a K that is more than 1. Does that make sense, class?
A little, Professor.
Okay, so maybe this one will tell you more. So if you have more products compared to the reactants, your K is more than 1. Okay. So the way that you're going to do it here is if you have a value of K, it can tell you, okay, which side has more. So if K is more than 1, that means your numerator is greater than the denominator. If K is less than 1, what does it mean? Your denominator is greater than the numerator. When K is equals to 1, what's the meaning of that?
There are equal amounts of products and reactants.
There are equal amount of products and reactants, or the system is in equilibrium. Remember the notion of equilibrium? The concentration of the product and the reactant remains constant. Okay, and the forward and the backward reactions are the same. So these are the information that you can obtain. So how do you know it's more K is more than 1? So the numerator is greater than the denominator. How do you know K is less than 1? The denominator is greater than the numerator. Again, it's the math concept thing. Okay. So if you're going to look at this, we could just say K is defined by the quotient between the products and the reactants. Now, it's very important to know this concept so you can make the necessary changes to, let's say, favor one reaction over the other. So if you want something, let's say, in the product side, and the system would what we call achieve equilibrium after some time, what do you need to do so that you can always produce the product that you want? Or if the product that you want is on the reactant side, what do you need to do so that you have more reactant compared to what we call the product? Okay. Now, how are we going to, let's say, do this equilibrium expression? So I'm going to get away from what we call the handout that I have and going to use the whiteboard to discuss your stuff about how are we going to write this so-called equilibrium expression. So for instance, we have this, right? N2O4 producing NO2, 2NO2. So how do we express the Kc there? So it's always products over the reactant. So NO2 squared over N2O4. Now, what if we do it like this? I want you to write the equilibrium expression for this reaction. So how are you going to write it? So all of them in gaseous form. Anyone? How are you going to write the Kc for that? Anyone? So what do we do here? What will I put on the numerator?
You would put the concentration of the product. So that's the CH3OH.
Very good. And you divide it with, how about the others? What
H2 and CO.
what else?
CO.
What is the one missing here?
Do you have to raise H2 to the second?
Very
Power.
good. So these are part of the multiple choice questions that's going to be asked. Okay. Question on that? We will have more example as we go on. Okay. So as you could see here, gas, gas, gas. So we could say they have the same physical states. So in this case, we have what we call a homogeneous equilibrium. So this applies to reaction in which the reacting species are in the same phase. So in this case, they are what we call gas phase. Okay. So if we're going to look at this, in addition to Kc, maybe we can also express it in terms of Kp. Why? Why do you think we can express it in terms of Kp? Anyone? Why can we express it in terms of the partial pressure So if you have Kc, C here means concentration, not constant. The C here means the equilibrium concentration. P here is the equilibrium pressure. Why do you think we can write this in terms of pressure? The answer there is because you
Because
are,
it has to do with gas.
it's in gas. You know, only gas exhibit pressure. Okay, so if you have the gas phase, you can alternatively write it in terms of Kp. Now the question is, what's the relationship between the two? Are they the same? Is one greater than the other? Okay, so if you're going to look at the relationship between the two, in most cases, they're not the same. Okay, so how are we going to relate the relationship between the two? Maybe we go to the general equation, the A of A plus B of B producing C of C and D of D. So if we're going to look at the relationship of Kp and Kc, this is how they're related. So we say Kp is equals to Kc times the gas constant times temperature raised to the n. Now the question is, what is this raised to the n? So that's the moles of the gaseous products minus the moles of the gaseous reactants. Now, if this is the relationship between the two, which I would suggest you memorize, when will Kp equals to Kc? In what case does Kp equals to Kc?
Gas.
No.
I don't know.
In a closed system?
You look at the equation here. When does Kp equals to Kc? When this one is equals to what? 1. And when does RT equals to 1? When delta N is equals to
0.
okay, 0. Any number raised to 0 will give you what?
1.
1. So when does delta N equals to 1? Or when does delta N equals to 2? When you have the same number of moles of the products and same as that of the reactant. So when you have the same number of moles on both sides, okay, gaseous products and gaseous reactants, so most likely your delta N is equals to 0. And if this is equals to 0, that's just equals to 1. And in that case, Kp will be equals to Kc. Now, how does Kp related to Kc? What's the law that binds them together? Anyone? What's the law that binds the two together? So what's the law that binds pressure with concentration? Are you familiar with this? What is this?
Ideal gas.
Okay, that's the ideal gas law. So how are we going to relate the two? Isn't this your concentration? So if we're going to express, let's say, A, so the way that you do here is just NA RT over B. And if we relate it with B, so this is just NB times RT over B. So how do we express Kp? It's the partial pressure of P, okay, raised to the B, right? Over partial pressure of A raised to the A. Do you follow that? So this is where you have A of A producing B of B. You follow this one, class?
Yes, Professor.
Kp is just equal to the partial pressure of your products raised to the coefficient of the product divided by the partial pressure of your reactant raised to the coefficient of that reactant. Now, what if I'm going to replace those expression with the one here? Do you follow this? So what if I'm going to simplify it in such a way I have an NB of B over NA of B, and then I have an RT here that is equals to B minus A. You still follow? So what will happen to this now? So Kp, N over B is equals to what? The concentration of B over the concentration of A, and then you have now here RT, B minus A is your delta N, right? And what do we have now? B of B here. There's still an over A here. So what is this equal to now? That is your Kc. So I just derived to you the relationship between the two on how we end up with this relationship here. So let's try. So we have also homogeneous equilibrium when we're dealing with this one. It's not only in the gases. When you have this so-called aqueous system. But here, if we're going to follow the law of mass action, we're just going to write all products divided by all reactants. But as you could see here, there's a liquid here. How does it affect the expression? So usually, since you have a liquid here, you could say it's a constant. Okay? It will not change during the reaction. So what you do, you can incorporate this one to the Kc, and you end up writing it as just this, only including the aqueous system. So if you're going to look at the aqueous system, the Kc that you have here is just the Kc prime times the water, where you incorporate the constant. And you don't use the so-called units because K is just what we call a ratio or a quotient of the reactants and products, usually products over reactants. So let's try to solve problems. Or before we solve problems, let's do the expression here. Anyone?
Wait, Professor, could you go back just for a second, please? All right, thank you.
You said you're not taking notes. So let's try. How are you going to write the equilibrium expression? Knowing this would give you at least what? 2 points or 3 points, whatever is the numbering of points in multiple choice. So try. Letter A, anyone? So it says here, if KC and KP applicable. So letter A, are both of them applicable?
Only KC.
Only
KC.
KC. Because you don't have there any
You don't have any gas.
gas. KP is just applicable on gas. Okay. Now how about B? Are both applicable in condition B?
Yes.
Yes. Okay. So later on, we're going to write the KC and the KP value. And I want everyone to participate in class, because if you still don't make it in the second exam, then that's where you have to worry. Okay, right now, I'm not worried, but after the second exam, you still get the same score as your first exam, then that's the time you have to think about. Okay. The last one. Are both of them applicable? Are you going to write both the KC and the KP, or just KC or just KP?
Yes.
Only KC.
Okay, it's just KC. KP is only applicable if you have a homogeneous system of gas. But if it's an aqueous solution, it's just KC. Okay, so now it's about time for us to write. So how do we write the KC for the first one? Anyone? I want you to participate, because this is one way for you to learn. So what will I put in the numerator, and what will I put in the denominator?
Concentration of H3O times F, concentration of F, divided by concentration of HF.
There. Question? Anyone? How about the second one? How do we write KC?
It would be concentration of NO2 squared
Okay.
over concentration of NO squared times the concentration of O2.
Now KP. How are we going to write the KP? So instead of concentration, we're going to use the partial pressure. So we just follow what we have in KC. So partial pressure of NO2 squared over partial pressure of NO squared times partial pressure of oxygen. Everyone follow that? Questions so far? Yes, Chino.
It's in a yellow, but Professor, are solids also expressed, or are solids also expressed if they give you something?
You wait for that. We will go on that. Don't get too excited, okay?
Oh.
Any more question? So the next one that we have here, how are we going to write this? The concentration of whatever this one is, right? Divided by the acetic acid and the ethanol. So you have there the acetyl methoxide over acetic acid and ethanol, or ethoxide, methyl ethoxide. Question. Now, we go on problem. So you're given here the equilibrium process, 2NO reacting with O2 to produce 2NO2. And in one experiment, the concentrations of the reacting species at equilibrium are found to be this. And you are asked to calculate Kc. And I would suggest let's include Kp. So how are we going to do this? So I think this is pretty straightforward, right? All you need to do is do the expression first. So Kc is equals to what? I think it's the previous problem. Okay, there. So NO2 squared over NO squared oxygen. So this is pretty straightforward. All you need to do is replace the given value that you have. So this is what? 15.5 squared over 0.0542 squared times 0.127, right? And what do you get? What do you get? I have been doing the calculation.
Got 6.43 times 10 to the 6, 10 to the 6.
The 10 to the 6?
10 to the 5.
How about the others?
Still calculating.
So I want you to participate because the one that's always answering, that's the one who topped your first exam. How about the others? What did you get? Still the same?
I think I have 6.4 to the power 10 times to the power 5.
Yep. So this is the answer. 6.43 times 10 to the 5. Anyone? Any question? Before,
Is it not 6.44?
what's the number after 3 here?
9?
Oh yeah, that will be 4. Thank you. So 3 significant figures because you have 3 here, 3 here, 3 here. So the final answer should be 3.
Professor, what is there any unit? I know.
What's
Is there
the-
any unit? No.
What?
Is there any unit? The unit though.
What did I say? The K doesn't have any unit. Now, KP, how do we get the KP? I added what we call additional question here. So for you to answer this, I don't have a calculator, so I'm going to rely to you to get what we call the answer. So to solve this problem, you need to get the relationship between the two. So Kp is equals to Kc times Rt raised to n. So you have here 6.44 times 10 to the 5, right? Then you have here R, so you can use here. What do you think you used in the R? Is it the 8.314 or the 0.0821?
Would it be the 0.8?
I have a question. So I
Okay.
already know how to get the answer, but my thing is like, how do you know like when to put it to a certain power? Like, you know, how you put, 10 to the 5th power. Like, how do you know? Because I know sometimes it's different.
It has something to do with your calculator. So the way that you're going to do it in most calculator, you put 15.5 and then
Up
raised
to
to the 2 or 15.5 times 15.5, just to be sure. Divided by 0.0542 times 0.0542 times
Oh, so
0.127.
type it twice instead of putting the second power.
Well, that told you, it depends on the calculator that you have, because you can put right away 15.2 and then raise to the 2.
Yeah, that's what I did, and I got 6.6439. But it usually, like at the end, it would have like a E, and it would tell me.
Well, you have to look at your how your calculator is.
Okay.
I have a question. It's similar to hers because when I do it, I get the it gives me the power, but the power is wrong. So like,
well,
if
did you put? I don't know how to solve this one because it's
no,
how you use the calculator.
I'm not saying for this problem, but I'm saying there's problems on Alex that I do, and like when I get the answer, it gives me the power as well, but the power is wrong. So should
So
I just
maybe you have to make sure that your input is right. Because the thing is, if you input it wrong, the output will be wrong. So you have to double check the calculation that you have. Because I realize some of you, most of your problem in the second exam is your calculator. Because you place your number in the right way, and then after all of a sudden the number just way off. That's what I observed. So try to go the numbers that we have here, input it, and the number should give you this answer: 6.4 times 6.44 times 10 to the 5. If you say it is different, then try to look at the input number that you have. Maybe missing this 0 here, this extra 0 will already give you an answer that is very far from 6.44 times 10 to the 5.
Okay, I'll see you next time when I do the homework.
Because I don't know what calculator you use. So it depends on the calculator that you use
I'm
also.
using a Casio, and I just did the problem twice, and it's like it still gives me the answer, but not like the power. I don't know why.
Oh, maybe the way that you do it is they do the calculation. I don't know how to resolve this thing. So maybe during the recitation, you show me how you use your calculator. That's the best way to resolve that thing.
All right.
Okay? So we're going to use here the Kc. So we're going to use the 0.0821 because this is not an energetic problem. And then the temperature that you have here, so you have 230, you add it with 273 because this is in Celsius, you need it to be in Kelvin. So that's 503. Now the question is, what's delta N? What's the value of delta N that we have here? Anyone?
Is it 0?
It's 2 minus 1, 2, 3. So you have a negative 1 here. What's the other way of writing that? 6.4 times 10 to the 5 over whatever the answer that you get here. And what's the number that you will get? I know where I get the calculator. Is this how you did it? I don't know if you could see at the beginning. So I input there the 15.5 and then squared and then divide it. And then if I'm going to get the answer, I got 643, 96, 3. So you consider the comma and the dot. So this is a Casio one.
Yeah, I see that. That's what I got. But then,
Yeah.
you know,
So
when-
why do you say the power is that equals to 5? So if you're going to move it, you're going to count. So if you're going to have the answer here, 6. So how do you express it like that? 1, 2, 3, 4, 5. So you have 6.4 times 10 to the 5.
oh, okay, thank you. I understand now.
This is Gen Chem 1. It resolved the problem? No? So let's
Yes.
try this one. Good thing there's a calculator here in the department. So I have 6.4 exponent 5 divided by 0.0821 times 503. So I get, so again, this will come out like this. Right? So if I'm going to round it up, 1, 2, 3, 4. And then I need what? 3 significant figures. So this will be like that one. Did you get that? Those who have problems with calculator earlier? Did it resolve your problem? So the answer is 1.56 times 10 to the 4. So that is what we call the Kp. Now what can you say here? This is 3, this is 2. Right? So question, before we go to the next problem. How about this one? So you're given Kp, the equilibrium constant Kp is found to be 105. So if the equilibrium partial pressure of PCl5 and PCl3 are 0.875 and 0.463, what is the partial pressure of Cl2? So the way that you're going to solve the express your Kp, and this is equals to what? Partial pressure of Cl2 times partial pressure of PCl3 over partial pressure of PCl5, right? Did you get that?
Yes.
So the next thing that you're going to do is substitute the values that are given. So what are given? You have the 105 or 1.05 equals to, what's the one given? You don't have the PCl2, but you have the 0.463, and you divide it with 0.875. So rearranging this one, what will happen? PCl2 on one side, so it equals to 1.05 times 0.875 divided by 0.463. Try. So the answer that you get there is 1.98. Everybody got that? Class, I hope you do your stuff. Okay.
Okay.
If your hand is doing it, it will be easier for your brain to absorb it. If you're just watching it and you're doing nothing, then there's nothing really that what we could come out. Now, what if I ask you to calculate also for the Kc? So we go back to the definition. Kc is equals to, oh no, it's not Kc, it's Kp equals to Kc RT delta N. So as you could see, the temperature is always given for that. So all you need to do now is what? Kp, Kc, RT delta N. So you want Kc. So you divide both sides by RT raised to the delta N. So you have here Kc is equals to the 1.05. No, it's 1.05 divided by 0.0821 times, what's the 250 equivalent from this one? Oh no, this is 230. So 250 plus 273. So that's 523. What is delta N? What's the value of delta N?
1.
Okay, it's 1 because you have 2 here and then 1 here. So if you're going to do this, 1.05 divided by 0.0821 times 523. So you have here 245. Everybody get that?
Yeah.
How about this one? So this is just a
Wait,
direct.
sorry, Professor, what did you get? What was the answer to the other question? Jesus, what? Wait, hold on. Professor, you used 1.05. Oh,
0.0245. Question?
never mind. Thank you.
I still express it in 3 significant figures. Now the next one is just a straightforward thing, the Kp to Kc thing. So Kp is equals to Kc times RT delta N. So you really need to know this formula. Okay, so you don't have the value of Kp, that's the one being asked, but you have the Kc here. And how are you going to do this one? So 0.0821 times the temperature is 220. So 220 plus 273. So that's 493. And what is our delta N here?
-1.
Okay, so it is 1 minus 2, 3. So that is a minus 2. Did you follow?
Okay.
Because
Is
you have 1 here, then you have 1 and 2. So 1 minus 3 will give you negative 2. So
all
you
right.
can,
My thing. Oh, yeah. I just wanted. I already know how you got 10.5. It's already in the question. It's just how did you get 0.821?
that's the
times?
R.
Okay, that's the R. Okay.
So that means whenever we have, okay, how should I say this? When we use that formula, we're gonna always input RT as 0.00.
Yep,
Okay, thank you.
because it's not an energetic problem. It's a gas problem.
Oh, so it only works for when we use it for gas problems. Is that what you're saying?
Yeah, because that's a
Okay.
gas constant. Okay. The 8.314 is if you have a joules in your unit, but this doesn't have any joules. So you use this R value. Okay, so you can also arrange it like this. So if you do that, 10.5 divided by 0.0821 times 493 and then squared the whole thing. So what do you get? Just want to make sure if it's the same as the one that I have.
I got
6.41 times 10 raised to minus 3.
Yeah, that's what I got too.
Okay, very good. Yeah, that's what I want everyone to do. You do the calculation real time. Now, to the question that Chino brought, what about if you have solid? So this is the instances when you have a heterogeneous equilibrium. What we have discussed so far are homogeneous equilibrium, either gases or aqueous. Now, what if you have more than one? So we have here the so-called heterogeneous equilibrium, and it applies to the reaction in which the reactants and products are in different phase or phases. So for instance, if you have it like this, what are we going to do with the solid? Okay, if we follow the law of mass action, So the law of mass action is just telling you to write whatever you have in the product side, divide it with whatever you have in the reactant side. You end up with this one. But as you could see, if you have a solid, what does it mean when we have a liquid earlier? They're both constant. So if they're both constant, you don't include it in the expression. Okay? So you end up writing only CO2. What happened is you're going to incorporate this one to the other side. And since they're constant, they will remain constant, but they give you the equilibrium constant. And you can also express Kp there as just the partial pressure of CO2. So you don't include solid in the expression, just like you don't include liquid in the expression. Okay? The concentration of solids and pure liquids are not included in the expression for the equilibrium constant. Now, how do we picture this out? Let's say we have the reaction system like this one. So what do you have there? The calcium carbonate, okay? If you allow it to react, it produces calcium oxide. And then, where does the CO2 come in? You look at the difference in there. What we call pressure. Because what happened, okay, the partial pressure of your CO2 does not depend on the amount of the calcium carbonate and the calcium oxide. It depends on the amount of the CO2 itself. So you don't include solids and liquid. And we have some seat work for those types like this one. So how are you going to write the equilibrium constant expression Kc and Kp for the following system? You still follow what you did earlier, but you just don't include the solid. So how are you going to write the Kc for the first one?
NH3 squared divided
The
by
concentration of NH3 squared times
H2S.
That's it. You're done. You don't include this one. And if you're going to look at Kp, it's just the partial pressure of NH3 squared times the partial pressure of H2SE. You don't include this. So how will be your Kc here in the second one? Anyone?
Would be a concentration of Ag times concentration of Cl.
That's it. You don't have a partial pressure because there's no gas. Now the last one, you have a Kc and a Kp. Now how are you going to express this? Anyone?
Is the Kc, is it 1 divided by Cl2 raised to the 6th?
Very good. So if you have this question, can you assure me you get it right?
With more practice.
Yeah, that's why you have the review.
Definitely.
I would like you to start using the reviewer that's given to you. It has the answer key, and in addition to the answer key, it has some short explanation on why you get the answer. So Kp will be equals to 1 over the partial pressure of Cl2 raised to the 6.
Professor, I have a question.
Sure.
So in this, and for C, we don't use the 4PCl at all. It's just the 6 we use, 1 over 6, the Cl2.
Yeah, because this is what? This is liquid and this is
Solid.
you don't
Okay,
include
so it's
them.
just-
The only one that you include is either the gas or
The aqueous. Okay, thank you.
So we're pretty much writing what the question is asked, right?
yep.
Like if it's looking for a liquid, then we put the one that has liquid. If that makes sense.
No, you don't include the liquid.
No. I'm not saying we don't include liquid. I'm saying we write what the liquid stands for, like 4PC I to the third.
No, I mean the 4PCl3 here that says it's in liquid form, but since it's in liquid form, it's a constant still. So if it's a constant, it's not part of the equilibrium expression. But assuming that this is a gas, then you can do it like this. Assuming it is a gas.
Okay.
But the thing is, it's not a gas, so that's why you don't include that one. So it end up like 1 over Cl6.
Okay. Thank you.
Okay? Now, how about if we have a problem like this one? How are we going to calculate it? Consider the following heterogeneous equilibrium: calcium carbonate producing calcium oxide and CO2. At 800 degrees Celsius, the pressure of CO2 is 0.236 atmosphere. So calculate Kp and Kc for the reaction. So can we say Kp is just your partial pressure of CO2, which is 0.236, right? Can we say the answer there is 0.236 already?
Yes.
Because that's the only one that you have. Now, how about Kc? So here, you're going to look at the relationship of Kp equals to Kc, RT, delta N. Now, the question now is how are you going to get the delta N here? That's the reason why it's here. The delta N is equals to what? Anyone?
Would be the moles of gas in the products minus the moles of gas in the reactant.
Yeah, so what would be delta N?
It would just be 1.
1. But to tell you frankly, why is it 1? It's because of this and this alone. You have a 1 minus 0, not 2 minus 1. You only include the gas. Are we clear on that? Class?
Yes.
Because
Yes.
this is the source of confusion. Where did we get the 1? Because 2 minus 1 is equals to 1. But it was clear that the delta N is just the difference of the gas products minus the gas reactants, the number of moles that they have. Claro? Clear?
Yes, Professor.
So if we're going to solve this thing, so it will be Kc divided by, how do we do it, this one? So we want Kc on one side. So this is just RT n. So you have 0.236 divided by 0.0821 times, what's the temperature? 800. So 800 plus 273. So that's this one, right? And raised to the 1, which is okay if you don't write it. So what do you get?
2.68, 2.678.
2.678 or 2.68 times 10 to the
Negative.
Did you get that?
Yes.
So question.
Yes.
Yeah, sure.
How do you get 1073?
Where's that?
Right there next to 0.0821
You see
times.
what I'm writing here?
Okay.
You're given the 800 degrees Celsius. You want to convert it to Kelvin.
Okay.
So 800 plus 273. That answer your question?
Okay. Yeah.
Question. So I think we will have the exam on 23rd. Or which one do you prefer? 30? You want to prolong your agony?
23rd, please. Let's get it so far.
Helps us with memorization, Professor.
I think 23rd is fine.
No, we're going to finish everything next on chapter 14 next meeting. So I let you decide. Maybe next week we can still decide when you want it. But the thing I'll ask to you is please do your part. Because what I'm going to do is maybe I'm going to post like a PowerPoint recorded slide, like one problem, and then showing you how to solve that problem, which I did already in chapter 11 and chapter 12. Okay. Now you ask me if it's still what we call the you can still pass the course. I can tell you, you're the best person to answer what we call that question. Because what I do is, on my part, I make sure that you are given all the materials that you need to prepare for the exam. So it's up to you if you want to dig it or just don't study. Because I can tell you, to pass the course, you have to learn. You cannot just pass the course by just what? Guessing the answer in the what we call the multiple choice question. And as you could see it, the way we solve the problem, the way the problem I gave you, there's a systematic way on solving them. So if you just do your part by practicing that thing, then I think you'll be okay. Okay. Now, I'm not surprised with the exam. The exam that I have is the same first exam that I usually give every semester when we are in the in-person class. but I'm not surprised with the average score that we have. Okay, so maybe I would suggest as early as now, you go over the reviewer that we have. It's always been there since the beginning of the semester, and try to start answering the questions that you have there. Because if you're going to do everything on the week of the exam, I'll tell you it's going to be a hard battle. And if you are the type of students who do it at the last minute, you're not going to make it, unfortunately. Okay. And there are your what we call Alex to help you. The idea that we have there is after we're done with class, you do Alex at your own time. Okay. So the question that will that you will encounter there that is similar to what you have. So I'm hoping that maybe if you're going to learn something from the exam that we have last time, it's a wake-up call on your part that you cannot do it the easy way. But I will try my best to help you. Okay. Because an average of 40 exams is also a reflection that is something wrong with the instructor. And unfortunately, this is what I can tell you. The second exam is the easiest exam among the 4 exams. That's why if you're still going to be problematic in the second exam, then I will give you the bitter pill of asking you to withdraw the course. But if you do well on the second exam, most likely you'll do well on the succeeding exam. That's all advice I can what we call give to you. Okay. So question. Before we go on some problems from chapter 13, because it's a recitation time now. Yes. Yes.
Sorry. Professor, I don't know, but could you go over the quiz that's talked about reaction order? Because I wasn't here when you talked about it, and I didn't know what it was talking about.
I don't know what the quiz is all about.
No, the one for today, it says something about reaction order.
Anyone wants to answer that question? Because explaining it to your classmate is one way for you to understand the concept, what the concept is all about. Anyone?
All right, I know how you do KP, how to solve for it now, which is a good thing. Can you just go over how to like solve KC one more time? It could be
So
any.
Casey from KP, you mean?
Huh?
Is it Casey from KP?
Wait, so it's not 2 separate formulas?
No, I mean, you can have just the Casey as a stand all, or
Yeah,
you can get
I
Casey
just want
from
the
KP.
KC. I know how to do the KP now. I just want to know how to do the KC. Can you go over it one more time?
Okay, so where's the... So this one is the one that is, as of today, you should know by heart. Okay, so you play around with that. KP equals to KC. So you want to get this one, right?
Yeah.
And you're given KP.
Yeah.
Okay, so you do the math. You want to isolate this on one side. So what you do, you want to eliminate this one. So in eliminating it, you're going to divide both sides by so you have here now KC is equals to KP. over RT delta N. You got it now, Denisha?
So just cancel. So to get KC, you have to cancel out RT.
RT over N. So you
over-
divide both sides, whatever number that you need to cancel it.
Okay. All right. Thank you.
Professor, you didn't answer my question.
Because I'm looking at the question yet.
I didn't know, sorry.
Okay? Because I don't know what the question is all about. Okay? You didn't give me the exact question.
Oh, should I give you the exact question?
Yeah, because I don't know what the question all about. Because it's all about chapter 13.
Okay. Okay. It says for a certain reaction of the general form, small a, big A equal products. A plot of the experimental data is A versus time is linear. What is the reaction order with respect to reactant A?
Can you repeat it again?
It says for a certain reaction of the general form, small letter A, big letter A equals product. A plot of the experimental data is A versus time is linear. What is the reaction order with respect to reactant A?
Okay, anyone can answer that question? If you have a certain reaction in the general form of A producing product, you have what? A versus time. Come on, class. We did this at the beginning. What's that order? There's a zero order. The answer there is zero. If it's ln of A versus time, then that's the first order. If it's a plot of 1 over A versus time, that's the second order. Any more question? So I have some problem here. So as I've told you, I'm focusing on chapter what we call 13. So one problem that will come out is determination of the so-called rate law. If you recall what it is, okay? So the one that I have is a problem like this one. I'm going to share, where is it? Control F. Share screen. Still remember this? 2 weeks ago? So most likely it will be in this form of rate equals to K raised to the maybe NO to the X and oxygen to the Y. So how are we going to solve this? Anyone still remember this?
You have to find the equal concentration for the experiment of each.
Okay. So maybe this one and this one to get, let's assign X to the NO. And then this one and this one for the Y. Because this one and 2, you have changing X with Y as constant or oxygen as constant. And then this one, you have changing oxygen with NO as constant. So the way that we're going to do is this is what? 0.250, 0.0250 over 0.0125 equals to 0.112 over 0.0281. So you end up with what? This is 2x and this is equals to what? 0.112 divided by 0.0281. 4. What should be the value of x? So that 2 raised to the x is equals to 4.
2.
Okay,
X is 2.
2 raised to the 2. So x is equals to 2. So maybe you could put there now that that's 2. And then for the other one, so you have 0.0506 over 0.0253 equals to 0.0561 over 0.0281. So if you have this, this is equals to 2. And I think that's also equals to 2. So 2 raised to the y is equals to 2. What's y? Okay, y is equals to 1. So rate is just equals to k NO squared over oxygen. Now, it is only a coincidence that they have this number here, okay? You didn't get that number from here. Because you might ask me, Professor, isn't it the coefficient? No, it's just a coincidence that they have the same coefficient as the x and y value that you obtain. So the next question that we have, the rate constant. So how are we going to solve for the k? So all we need to do, we use this one. So this is the thing in the exam. If you end up wrong with this one, so most likely you end up wrong in the second question. Okay? That's why you have to be very careful. So given this one, rate equals to k, NO squared times oxygen. So all we need to do is, if we want to get the k, we divide both sides by NO squared times O2 because we want to eliminate this thing here. So we eliminate it by dividing it by that number, but that expression also. So we have here k is equals to rate over NO2 squared over O2. And all we need to do is just substitute it with the rate. So you have here, so if you're going to use experiment 1, use experiment 1 values only. If you're going to use experiment 2, you just use experiment 2 values only. If you're going to use experiment 3, just use experiment 3. You don't mix them up. So if I'm going to use experiment 1 there, so I have 0.0281 divided by 0.0125 squared. And this is 0.0253. So if you're going to get the value there, 0.0281 divided by 0.125 squared times 0.0253. So the value that I get, I just want to double check. What the value that you get? 7.11 or 711? Oh no, 7.11. That's what you get?
I
Hello?
got 708.
That's for the second one. And the third one, I think, would be around 7.10. But at least they're close to one another. So this is a 10-point question in the exam. Because the way I look at the example is either you understand it or you don't understand at all. Let's try another one. So question here before we move to another one. Because we want to utilize until 12:30, so I will give you time for your second portion of the quiz where you do calculation. So now let's go here. So you have here,
Professor.
yeah.
So Eric, to find the weight order, it has to be something raised to power x or something raised to power y, right?
What?
For this x and y, you have to like say the answer raised to power x, right? X cannot be like a whole number, like a regular
X
number.
and Y should be whole number. I want you to look at the recording, okay? So let's go on this one. So this is another type of questions that may come up in your exam. So this is an integrated rate law. Isomerization of cyclopropane to propene is first order with a rate constant of 9.2 per second. If the initial sample is a concentration of 6, what will be the cyclopropane concentration be after 1 second? So this is a first order. So you need to know the equation. So this is just what? Ln of A T over initial A equals to negative KT. So what's the one being asked? The one being asked is the concentration after some time. So you can put the Ln of A. This is divided by what? 6 molar. Am I right? And this is negative. So what is K? 9.2 per second. And you have 1 second. So if you have that, that will be a negative 9.2, right? Do you follow?
Yes.
How do we eliminate Ln? We put E, raise it to negative 9.2, so this one will cancel out its Ln. So E raised to the negative 9.2 will give me 1.0 times 10 to the 4. Or since it's not yet the final answer, 1.01 times 10 to the negative 4. And I multiply the 6 on it. So that will give me my concentration after some time. So times 6, so that will be 6.1 times 10 to the negative 4. So that's the answer to my question. Question? Question? And the last that we have here is the half-life. Oops. Oh, I didn't put the question here. So I'm going to go with the question on the half-life. Where's that? Oh, it's here. Forgot to share this one. So for the half-life question, we have this problem. In a solution that is 10 molar in ammonium ion, the reaction is first order in nitrite ion, and the rate constant of at 25 degrees Celsius is 3.0 times 10 to the 3 per second. So you are asked, what's the half-life? So again, this is what? First order. So what's the equation for the half-life for first order? T1/2 is equals to
ln2 divided by k.
0.693 over k. So all you need to do is just get the value of 0.693, divided it by the given value here, and you get the half-life value. So I get here around 2.31 or 2.3 times 10 to the negative 4. So that will be seconds. Do you want a quiz before or in addition to the quiz that we have after we call it a day? You want the quiz in between? Anyone?
Yes, Professor. It'll help.
Okay, so I'm going, somebody will remind me maybe on Monday.
Hey, please, can you go back, please? I didn't take a picture.
So question, before I open up the second part of the quiz. So the second part of the quiz are all, we could say, calculation. So you have 3 questions there. So one of them is very similar to what we have right now. And even though there are what we call calculation, only one of them is the one that you supply the answer. The rest are what we call multiple choice. So I want you to follow instruction, especially on the one that is the calculation where you have to write the answer. So there's what we call, their calculation, but two of them are what we call multiple choice. So I'm going to give you 20 minutes for that. You think that's enough? Is that enough for you to search the internet? Question?
Yes, I have a question.
Okay.
So like, how did you get 0.693?
0.0693, that's a given one.
Oh, it's given?
That's
Okay.
the, if you're going to look over the lecture that we have, that's what we call given. That's just the ln of 2.
Okay, all right.
Okay.
So with like next problems we get, it will always give us a given, right?
Yeah, but the 0.693 is not a given. It is part of the formula.
Oh, okay, all right.
So that's the formula for the half-life for the first order reaction.
Oh.
So you need to know that. As you could see, it's not given there. It's just that the half-life of a first half reaction is equals to this equation. It's really, if we're going to look at this, T1 half equals to ln of 2 over K. But the value of ln of 2, if you want to check it yourself, okay, is what we call 0.693. So question before we call it a week? So I would suggest you start reviewing for your second exam. Start doing your Alex. Don't do everything at the last minute. I know you have a lot of things to do, but as much as possible, find some ways to do it. They say if there's a will, there's a way.
Professor, when is the test due?
30.
Today?
Which one? The second one, yeah, 1 o'clock.
Oh,
Any more question? Any more question? The other one? So please do the quiz before 1, because if you don't do it before 1, I have to do something.
Professor King.
I have to open it to accommodate your result.
Can we go over
Yes.
the finding the orders of reaction when you have 3 or more experimental values?
Well, you just do it 2 by 2. If you have more than what we call 3 experimental values, so you just focus on the one wherein one is double and the other one is constant.
So for example, in your last slide, you had NO3.
Yep.
You would, so at a constant concentration of NO3, you'd find the order
The other
of
one.
the rate reaction of the other.
Yeah,
Okay.
because the way that you look at this is you just look at the concentration of, let's say, A, and look at what's the rate of reaction. So if you double this one, what happened to this? And the B is constant. So if you have more than, let's say, what we call a C, then this one should also be constant. So if you have, let's say, A plus B plus C producing D plus E. So if you're going to do that, the rate is just equals to K raised to A, X, B, Y, C, C. So if you want to get this one there, the X, this is changing while the other two is constant, and see what happens to that one. If you want to get the Y, this one is changing while the other two is constant, and see what happened to the rate. If you want to get the Z, this one is changing while the other two are constant to see what happened to the rate.
Okay.
Question? So start taking your quiz. Yeah, that's I just mentioned. If you submitted it late, I have to do something to it. I have to open it so that you can see the score. Okay? So any more question?
Professor, did you upload the quiz because I don't
Oh,
see it?
okay. I think I have not. Okay. So it should now be open in 3, 2, 1. It's now available. Any more question?
No, thank you again.
Okay.
Have a good day, Professor.
Okay, bye-bye. Study, okay? Study, study, study.
Sorry, last question. And the quiz is October 23rd? I mean, the exam, sorry.
30.
October 30th?
Yep.
Okay.
October 30th. I don't know why you said you don't have a quiz. So maybe you're late. That's why I have to open it. Or you didn't take the quiz. So maybe you were caught by the deadline. So I need to do it. Okay. Yeah, Sumitra, I already opened it. If you don't see a score, so that means you were caught by the deadline. Okay, if you don't have any question, see you next week. Start taking the quiz now.